Yes, we saw you, Elijah. Just kidding. Okay. Welcome to chemistry, period 6. I like saying that. Okay, Bellward questions, page number something or other, 198. Letter A. Help me out with these answers. They are really simple. Number 1, metal, non-metal, or metalloid. Oxygen. Elijah.
Non-metal.
Okay. Number B, barium. Back.
Metal.
Number C, germanium. Like Eli. Germanium. It's really easy if you look at this thing on the back. Germanium? Oh, I'm sorry, I didn't hear the
He
A.
said it 3 times.
My bad, sorry. Letter D, iron. Chucky. Metal. Okay. Again, this makes it really clear. My colors up there are a little bit different, but everything blue here is a metal. Everything yellow here is a non-metal. Everything green here is a metalloid. And mine are different colors, but same pattern. Okay. Now, one thing I want to cover while we're talking about this question is something I didn't cover earlier this week. When we were talking about the properties of metals, you know that they are malleable. They conduct electricity. They are shiny. They are solids for the most part, with the exception of mercury, and they have certain characteristics. If you look at the periodic table, one of the trends that we see in the periodic table is something called metallic character. And we will generally say that the farther to the left on the periodic table that we are, the more metallic something is. And that kind of makes sense, because here's your nonmetals, here's your metals. Okay? So as we go across the periodic table, things become less metallic. And again, we go from metals to metalloids, which are kind of metals, but not all the time, to nonmetals. Okay? So metallic character decreases as we go from left to right. And that's something I didn't mention earlier this week, but you do need to know. Okay? It's one of the trends that we're studying in section 3 of chapter 6. Okay, back to the homework on page 198. Number 32A, match the following with the group number. Alkali metals. Savvy. 1. Sally, halogens.
Group 2. No. Group 17.
Group 17, good catch. Laney, alkaline earth metals.
Group 2.
Group 2. And Kristen Phillips, noble gases.
Group
Group 18, the one we haven't chosen. Yeah, good. Okay, everybody cool on that? Those are the 4 groups with special names, so you need to know them. Again, make sure you're aware of that. We will have our test on this chapter on Friday of this week, which means we will have Thursday to finish up our notes and review, and test on Friday. Special treat for you tomorrow, because I won't be here. Okay. Next, take your homework out, and let's go through the homework questions. Now, I understand I didn't teach you the stuff on these questions yet, but if you read the chapter, you should have been able to find most of these answers on your own. And it's going to lead us right into today's discussion of ionization energy. Okay? Number 658, what is ionization energy? We'll take it officially, but you've looked it up and written down on your homework. Savvy? Okay, and I'm not too concerned about the word gaseous atom, but it's the amount of energy required to get or remove or steal or take away one electron from an atom. We'll describe that and explain it later this period. Number 2, if an element forms a negative ion, on what side of the periodic table does that happen? Your choices are left and right. Negative ions. Elijah.
Shouldn't it be the right because it has to be a gas to ionize?
Well, every atom can ionize, not just gases. Okay? But you are right. These are going to form negative ions. These are all going to form positive ions. Metals are going to form positive ions. Non-metals are going to form negative ions. You say, what about the metalloids? Yeah. Depends what day of the week it is. Okay, in other words, they can do both. So it depends on the circumstances. Number 60. If we're talking about magnesium, calcium, and barium, which forms the ion with the largest radius? This was yesterday's lesson. I had 3 different elements here, all in the same group. Which one's going to be the biggest one, right? Okay, and which one's going to be the smallest one, Angela? Okay, now tell me why. Somebody raise your hand. Tell me why barium would be the largest of those 3 and magnesium would be the smallest. Savvy?
Is there a atomic number increases so that means you have to have more energy?
More energy levels, that's the key. Okay, more energy levels, bigger atoms. As we go down the groups, I add a 2nd energy level, a 3rd energy level, a 4th energy level, a 5th energy level. Every time I add an energy level, I'm literally increasing the size of the atom. You would expect it to. Okay, number 61. Explain why each successive ionization of an electron requires a greater amount of energy. And let me just give you the answer. If I have 2 electrons in the outer shell of magnesium, it takes a certain amount of energy to take one of those electrons away. What's going to happen after that? In order to steal the 2nd electron away, I've got to overcome a greater attraction. Remember, in the magnesium here, I've still got 12 protons. And those 12 protons are pulling on the remaining 11 electrons even stronger now. So every time I take an electron away, I have a stronger and stronger bond between the remaining electrons and the protons. So it's going to take more and more and more energy to steal each successive electron. Okay? It's easier to steal $1 from somebody or $10 from somebody. They won't miss $1. Right? They'll miss the $10 bill. Anyways, how does the ionic radius of a nonmetal compare to that of a compared to its atomic radius? Okay, nonmetals like oxygen. Okay, let's pick one here. So this question is saying, if I change this into an ion, is it going to get bigger or smaller? So here's oxygen, 2 + 6, right? 8 electrons. And I'm going to change it into an ion. It's missing 2 electrons. It wants to have 8. Always wants to have 8. Coming up on that question. So it's going to pick up 2 more electrons. Is that going to make it bigger or smaller? And why? Smaller? I won't ask you why, because that's the wrong answer. Because? No, not for these guys. I can't add enough electrons to add more energy levels. Energy levels come by adding protons, and that's not happening here. Why is this going to get a little bit bigger? Why is 8 electrons going to take up more space than 6? Oops. They repel each other. All these electrons are negative, right? They're all pushing away from each other as far as possible. And so I only have so many orbitals in there, right? And so if I got 6 electrons, there's some room to spare. We got some, we got some space around us. I get all those bedrooms filled up, what's going to happen? Everyone's going to push away from each other as far as possible. It's going to make things a little bit bigger. Okay, so it has to do with repulsion. R-E-P-U-L-S-I-O-N. Okay, next one. Explain why atomic radii decrease as you move from left to right. We covered this yesterday on this board right here. Why does the radius get smaller as I go across the row? Right? Okay, stronger force between the nucleus and that energy level of electrons in the outer energy level. Okay? 4 versus 4 is stronger than 3 versus 3, and so on. Number 62. 64. Now, in order to answer 64, we haven't covered this yet. If you have your textbook out, please turn to page 193. In the upper right-hand corner, there's a cool little chart that will help you answer these questions. We're going to cover it today, but the chart takes us to the very end, so it gives us shortcuts at the end of the story. It says ionization energy increases as I go from left to right and decreases as I go down. So I'll give you two elements. Figure out which one has the highest ionization energy, lithium or nitrogen. Both of those are in the same period, period 2. So this one's going to be higher. Hunter? 193, top right-hand corner. Nitrogen or lithium? Huh? Yeah, it's to the right, so they increase. Ionization energy increases to the right, so nitrogen wins. Okay, the next pair is krypton or neon. So those are both in the noble gas group. Addison? Neon's going to be higher because they get less as we go down. We'll talk about the why of that in today's class. And the last pair here is cesium and lithium, group 1. Higher, Sophie? Lithium, it's at the top, and they get less and less and less as we go down. Good job. Number 65. What is the octet rule? Elijah?
Atoms tend to lose or gain electrons to have a full set of 8 valence electrons.
Okay, everybody knows oct means 8, right? So octopus, octagon, octet. And everything in our noble gases has 8 valence electrons. So the goal of every atom is to get 8 electrons in its outer shell. Yes?
With the exception of hydrogen and helium, because they're completely held with 2 valence electrons.
Because they only have one s orbital, they can only hold 2. That's the second half of the question. Good. Hydrogen and helium are the exception. That actually has a name. Instead of the octet rule, anybody want to guess? Savvy, it's called the duet rule. Because it only holds 2. Did you say that? Yeah, it is. This is the duet rule instead of the octet rule. Just like when you have 2 people singing, it's a duet. If you have 8 people singing, it's called an octet. Okay. Put your homework away. Take out your notebooks. And let me quiz you a little bit on these fun polyatomic ions. I'm putting you on the spot. Here we go. I'm going to call on you. You have a chance to answer. Today I'm letting you cheat. You have your book open or your flashcards, good. If you didn't make some flashcards, you better, because these are going to haunt you the rest of your life. I mean, the rest of the year. Remember back in 2018, Mr. Gibbs, oh yeah, he made us memorize some horrible flashcards. Oh, I hated it. MnO4, I still know it's permanganate. You'll remember them. Okay. Kayla, CN. Cyanide. Cyanide, cyanide. Okay. MnO4. Thomas. Permanganate. NO2. Nitrite. Not to be confused with the next one, Mr. John Griffin-Bell. Nitrate. Right now, guys, they are in order. In a day or two, they will no longer be in order. So if you hear nitrite, you know the other one's going to be nitrate. If you know this one's nitrate, then the next one's going to be nitrite. Brian, Cr2O7. Dichromate, dichromate, di. H3O. Reed, you got these? Not yet? I know you've been out. Make some flashcards, make sure you know these. This is not in the book. This is the one I gave you. Right? Hydronium. It's water with an extra hydrogen, which basically means it's our acid molecule, okay? We'll cover it a lot in about a month and a half. PO4, Savvy? Phosphate, you got it. NH4, Sally? Yes. Keep coming. Ammonium, yeah. Okay, Daniel. Acetate. Laney. What's your baking soda?
Bicarbonate.
Bicarbonate. Good. You with us, James? Hydroxide. Nice. This is going to be all of our bases, which cancel out our acids. Eli, you got CO3. Just start here. Say, I know what that is. C.
Carbon.
8.
Carbonate.
Go ahead.
Carbonate.
Just like we had phosphorus gives us phosphate, and sulfur gives us sulfate, and nitrogen gives us nitrate. Okay? The oxygen gives us the ATE ending. Okay. Lucas. Sulfite. Good job. Because, Colby, sulfate. Everybody?
Sulfite. Sulfate. Sulfate. Sulfite. Sulfite. Sulfate. Sulfite.
Can't fool you. You're doing great. Practice those. Sophie. Good. Lorna.
Oh, hold on. Permanganate.
Permanganate. Yes. Elijah.
Nitrite.
Addison. Everybody?
Nitrite.
Everybody?
Nitrate.
Everybody?
Nitrite.
You ready?
Nitrate.
How about this one?
Nitrite.
How about this way?
Nitrate.
How about this way? Okay. Practice them 1,000 times till you got it. These are the ones that are going to kill you. These are the evil twins. Nitrate, nitrite, sulfate, sulfite. Okay? Okay, let's keep going here. We got Ashanti. Ashanti. Huh? Yes. Di something. Chromate. Dichromate. That's chromium. Dichromate. Kristen, you got H3O. Hydronium. PO4. Rat. Angela. Ammonium. Kayla. Acetate. Riley.
Bicarbonate.
Yes, Hunter. Hydroxide. Everybody. PO what? PO4. NO what?
2.
Nice. NH what? 4. CR? CR207. SO?
3.
H? HCO3. Remember the bi is on hydrogen? CO3, carbonate.
H3O.
Yes. HBO.
Oh.
OH. Like OH! Exclamation point. CO3. CO3, carbonate. NO. Yeah, I got half twos and half threes. NO3. Nitrite is NO2. NO3, NO2, NO3, NO2. SO4, SO3, SO4, SO3. CN.
MNO4.
Good. Watch your capitalization. Capital M, small n, capital O, 4. Okay. Practice those every day. Okay, notebooks out. Here's where we left off yesterday. We've talked about the atomic radius They get smaller as we go across the rows, and they get bigger as we go down the groups. Bigger because of energy levels, smaller because of attraction between the nucleus and the outer energy level. Then we talked about ionic radius. We finished up yesterday here talking about why does this make this weird jump in the middle. It gets smaller, 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 boom! All of a sudden they get bigger. So I just want to cover this one more time, make sure there's no confusion. The atoms on the left-hand side of the periodic table, and they've cut out, notice that all of our transition metals are missing here, so we don't worry about them. Okay, these are the ones that give away electrons. They're going to form positive ions. Everything in group 1 forms a +1 ion. Everything in group 2 is going to lose 2 electrons and form a +2 ion. Everything in the boron group is going to lose 3 electrons and form a +3 ion. Okay? And remember, when we lose those electrons, we lose a whole energy level. Let me go back over here. What happens when magnesium loses these two electrons? It gets smaller. Because now it loses a whole energy level and goes back to being like neon. It's happy there, it's not complaining, because now he's got 8 electrons in his outer energy level, but he's got a +2 charge, and he looks like neon. He's still got his 12 protons in the nucleus though. So the reason these are smaller than they should be, if I compared this, or this, whoops. If I compared this to the previous chart, which showed the size of the atoms, they're a lot smaller. It lost a whole electron, a whole energy level. Why don't these ones do that? Because remember, like oxygen here, we talked about on your homework, I'm putting more electrons in. So I'm not losing an energy level. They're actually, like Lucas said, they're going to push away from each other until they get the maximum size possible. So these are actually a little bit bigger than the atoms they come from. Everything that forms a positive ion is losing an energy level. Everything that gains electrons is staying the same and actually getting a little bit bigger. Now the trend that we saw on atomic radius is the same as the trend on ionic radius. They get bigger as we go down because we're adding energy levels. That doesn't change. These are bigger, these get bigger, these get bigger, these get bigger, these get bigger until here something weird happens. These get bigger, these get bigger, okay? So that's the same. And they actually do get smaller as we go across the periodic table. You can see 76, 31, 20, 15, 102, 72, 54, 41. Those are in picometers. Picometers, okay? Which is 1,000 times smaller than our nanometer. But something happens here, and all of a sudden they jump up in size. And that's because we go from losing electrons to gaining electrons in between carbon and nitrogen here. Everybody understand? Still decreasing in size this way, still increasing in size this way. But there's a big change where I go from +4 to -3 on the ions. Now a lot of times, guys, I will not quiz you or test you on what this group 14 elements do. Because sometimes they can form a +4 ion, and occasionally they form a -4 ion. And very rarely do they even form ions at all. Most of the time, this group right here, carbon and silicon, are going to form covalent bonds, which we're not talking about till chapter 8. Okay? They're not going to form ions, they're going to share electrons instead of giving away and gaining electrons. So don't worry about these guys. Don't worry about, oh, what really happens there, and I really want to understand it. Okay? Just wait, we'll get to it in a couple weeks. Okay? So, but you did need to know, +1, +2, +3, group 1, 2, and 13, -1, -2, -3, group 17, 16, and 4, 15. Okay, today we're talking about this. So ionization energy. Write it down in your notes. If you've already got it written down in your homework, I want you to get it in your notes. You've seen it twice. It's an important thing, okay? Somebody give me some synonyms for the word remove. So this is, how much energy does it take to remove an electron? Somebody give me synonyms. Savvy.
Take away.
Take away. Another one. Ashanti. Subtract. Good. Daniel.
Get rid of it.
Give up.
Get rid of it.
Give away.
Yeah, give away.
Yeah, that works. Give me another one. Glyden.
Steel.
I like that one. I'm going to use that a lot this period. Steel. Okay, another one. Synonyms for remove. Savage.
Erase.
Yeah, maybe. I don't like erase because it feels like you're annihilating it, and we know conservation of matter says we can't make it completely erased. So it's not erasing it, it's removing it. Lucas? Exile, good. Acquire, get. Yes, for the same reason I don't like erase, okay? We're not eliminating, we're just moving it somewhere else, okay? We're sending it away, we're kicking it out, we're exiling it. I like that one, that's cool. Yes?
Defenstrate.
What?
To remove by throwing out a window.
Bench.
Basically throwing it out there.
What did you say now?
Defenstrate. I thought it was defenstrate.
Spell it?
I think it's.
I've never heard this word.
I think it's
Okay, I'll take the word for it. Okay, let's talk about this for a second. I'm going to come back and explain this in a second. Let me get your attention over here. Let's talk about a couple atoms and understand why. Hey Elijah, you want to be a cameraman? You want to get that focused over here?
Oh, you're supposed to move it?
You just need to rotate it. Okay, let's talk about a couple things regarding taking electrons away from something. Ionization energy. Okay, two things we need to know. Number one, let's pick on sodium. Sodium's easy to pick on. He's got 2 electrons, 8 electrons, and 1 electron. Okay, is that going to be easy to grab? You can sit back down if you want to. Is that going to be easy to grab or hard to grab? Just one little electron up here. Okay. Read. Okay. Why? Why is it so easy to grab this electron from sodium? Sodium is one of the most reactive metals in the world. Lucas?
It's on the outermost mineral.
Yeah, he's way on the outside. He's available. Number 2, he's all by himself. And things that are all by themselves are vulnerable, okay? It's like the little sheep on the edge of the pack, you know, and the wolves in the woods looking out saying, who am I going to get? Is he going to run to the middle of a pack of 100 sheep and steal the strongest one? No, you're going to find a guy that's wandering over there close to the woods, pounce, drag into the woods. Okay? So that's the vulnerable electron. Very easy to steal 1 electron. Did I tell you about my bicycle already?
No.
So we lived in Santa Clara, about half a mile from where the new 49ers football stadium is. And the neighborhood's not super, but it's okay. It's middle class, but is crowded. And I bought my son, he's probably 12 years old, a nice $250 bicycle for his birthday. And, you know, like 15-speed kind of thing. And the first week he owns it, leaves it out in the driveway. 4 hours later, it's gone. Just gone, plain old gone. Okay? So what happened? Somebody walked by and said, it's available. I think I'll ride it home. And that's what happens. You got a single thing available, unprotected, nobody's watching out for it. It's easy to steal. Now, suppose I got magnesium here. It's going to take more or less energy to get 2 electrons.
More.
Okay, so now I got somebody walking down the street, 2 bicycles in the front yard. Okay, and I don't know if you've ever noticed, it's hard to steal 2 bicycles by yourself. It's very difficult to ride 2 bicycles by yourself. It's very hard even to walk 2 bicycles by yourself. I've tried it, okay? No, I'm not stealing. I never stole. But so here's you know, Jose walking down the street. Hey, Mom, you need a bike? Yeah, come on over. I got one for you. Okay? And so now he's got him to do a little bit of work. He's got to get somebody to come help him to get the second bike. It takes more energy to steal 2 than it does to steal 1. How about if we got 3 bikes in the front yard? Okay? More energy or less energy? More. Okay. So now the young man or lady has got to make multiple phone calls. Hey, does your sister need a bike? No. She just got one for her birthday. Oh. Hey, Mary, you need a bike? What do you mean you don't ride bikes anymore? And so now he's got to make like 18 phone calls to find somebody who can come and get a 3rd bicycle from your front yard. It takes a lot more energy to get that 3rd electron, right? Easy to get 1, a little more energy to get 2, more energy to get 3. Okay, so we got a different sitch now. Here's fluorine. Fluorine's got 7 bikes in his front yard. He's got a Huffy Pro. He's got a Lance Armstrong 24-speed custom-built thing from Europe. He's got a powder puff pink one for an 8-year-old girl with the basket in the front and the frilly things coming out of the handlebars. He's got a 3-speed off-road thing with the jacks, the shock absorbers, and the big knobby tires. He got a complete complement of different kinds of bikes here. 7 of them and 1 parking space in the front yard right there. Anybody walking by is going to say, man, it's too hard to steal 7 bikes. In fact, somebody might walk by and say, hey, you know what? I got the perfect thing to give right there. I'm going to give this guy an 8th bike to complete his collection. Now that might happen, but really what usually happens is, this is the guy that's stealing the bikes from this guy. This is the one that says, hey man, I need 1 more bike to complete my collection. I'm walking down the street right here, okay? So fluorine is going to take a huge amount of energy if somebody wanted to steal his 7 bikes, because he's got a security system. Okay, so a little bit of energy, more energy, more energy, more energy. Okay, let's talk about this. So this is a chart showing each of the elements, and let's see if this makes sense based on what we just talked about. I got hydrogen. It takes 1,300 kilojoules per mole. Okay, kilojoule or 2. And so 15, 16, 14, 1,300 here. Helium. Why is helium so much harder to steal an electron from than hydrogen? Elijah?
Because it already has a complete set.
Okay, so it's got 2 electrons in its s orbital. They're happy. They're complete. They protect each other. They're buddies. They watch each other's back, if you want to think of it that way, okay? So I can steal 1 electron from hydrogen easily because he looks like this. But to steal 1 electron from helium, again, there's 2 electrons in this orbital, and it's going to be a little bit more energy to steal that first electron. Now look what happens. It drops all the way down here for lithium. Why? Okay, what's lithium look like? Lone wolf. Okay, lone electron all by himself way out here on lithium. 2 in its s orbital, 1 electron, outer shell. How about to get 1 from beryllium? Here's beryllium. More energy, right? Just like helium. Why do you think this one for boron goes down a little bit? In general, the trend is up from left to right. But why would boron be just a little bit easier? Lucas?
Has an odd number.
But why? That's not really the reason. Why would boron Why would that electron be a little bit easier to steal than beryllium's? Ashanti?
Because it has the one electron outside.
One electron where? It doesn't. It's got 3. Boron does. What's special about that 3rd electron? Angela? Yeah, no, go ahead. No, but it. Kayla?
Is it because it's in its own orbital?
What kind?
Sorry, D orbital? S orbital?
And Sophie? It's the first electron in a p orbital. All by himself in one of these. Okay? All by himself out there. What? He's lonely. He's the first electron. Boron is the first electron in the p orbital. And so he's not connected to the s orbital electrons because he's got his own shape orbital. He's a little bit whacked out. He's got that funky shape, dumbbell shape, remember? He's all by himself. Doesn't have a roommate yet. Okay? So he's going to take a little bit less energy. And then where we go? Boron, carbon, nitrogen. 3 more electrons. What happens when I get to oxygen? We get a little another dip. Somebody help me out with this. Why is oxygen's electron going to be just a little bit easier? Savvy.
It's gonna be through each one of those, so oxygen will be the first one to the second.
Okay, so Savvy says each one of these dumbbells is going to have 1 electron in it. Who has their own bedroom at home? Don't have to answer, okay? It's peaceful when you have your own bedroom. I would gather anyways, I've never had mine. But 22 years at home, 3 years in college, and 30-some years of marriage, still don't have my own bedroom. That's okay. I'm not bitter.
Sad.
I've never had my own bedroom.
But things are peaceful because there's nobody to tell you to pick your socks up. There's nobody to tell you to put your stuff away. There's nobody to tell you, hey, close the door. Nobody to tell you, hey, you snore. Okay? But when we get that oxygen electron, what happens? You get a roommate. And it's not quite so peaceful. And it's easier to kick him out of the bedroom. Okay? It's easier for for him to run away. Okay? Because nobody's going to miss him. Okay? Go ahead, run away. I won't tell Mom. Okay? So he is a cause of unrest. Okay? So he's going to be easier to pick off and to get lost. And then we go up to fluorine and then neon. And then boom, all the way back down to sodium. Why? Boom, back here, 1 electron all by himself. And then we repeat the pattern. Watch. Sodium, magnesium, boom, aluminum. Why? P orbital. 3 p orbitals, boom. Sulfur, first roommate. And then chlorine, then argon. And then boom, back down to potassium. Now, what in the world is this? Somebody help me out. Right. Yeah, there's your d orbitals. Okay, there's 10 in there. 10 elements, each adding 1 electron, and what are they doing? Nothing. Yeah. Are they more energy to steal them, less energy? Oh, about the same, about the same, about the same, about the same. Now there's a little blip in the middle where you get 5 electrons. It's more stable when everybody's got their own bedroom. 1, 2, 3, 4, 5. We've got 5 orbitals. I add a 6th one, it goes up, or it goes down. And then when I get to 10, this one right here is the 10th one, that's nickel, real stable. All my d orbitals are full. And then what? Boom, back to the first p. Real easy to pick off the p. Okay, so now we're up to this one here. Gallium, germanium, arsenic. Then we drop down selenium, first roommate. And then bromine, krypton. Then back down. Repeat the process. Everybody see the pattern here? Pattern, 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 pattern. What is a pattern? A pattern is a trend. It's the way things are happening that sets a trend or a pattern. We call it a periodic property, ionization energy. What kinds of conclusions can we draw? I'll come back to this in a second. Let me jump ahead to the results. Number one, ionization energy increases from left to right. Now you saw the blips. You should understand the blips. This is blips when I go from S to P, and the blips when I start adding roommates in the P orbitals. But in general, increases left to right. Make sure you know it. In general, ionization energy decreases as I go down. What? Why is that? Let's talk about it. Elijah, can you get the camera again?
He doesn't trust me. I don't understand.
Okay, let's pick two elements in the same group. And let's pick, no, too much work. Magnesium and barium, okay? Okay, so both of these have 2 electrons in their outer shell. Magnesium, total number of 12. So I got 2, 8, 2. How about barium? 2, 8, 8, 8. There's more than this. There's a lot more because I'm not putting in my d orbitals and all those things down there. Okay? And then finally, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Another 8. And then another 2. Okay. And there's more than that because of the d orbitals. Okay? I'm just showing you the s and the p orbitals, which is all we can do with Bohr diagrams. Is it easier to steal these or easier to steal these? And tell me why. Rap.
Barium, because it has a less of a
Why?
It's far away.
Yes. Okay? So, that's one reason. There's going to be a second reason. First reason, look at the huge distance. Which one's easier to steal? The one that you leave by the sidewalk or the one that's in the garage with the garage door open? Sidewalk. It's so much farther from the house. Everybody goes, man, that's a gift. Right? If it's in the garage, you're taking a risk. It's a little bit harder to steal. Okay? So distance, absolutely. More energy levels, farther away. Secondly, anybody? What's in between? What's in between my protons and those 2 little electrons way out there? Elijah?
More electrons that are repelling.
How much?
I mean, repelling them away
4
from
electrons.
the sun.
How many over here?
9.
Try 10. I got 10 electrons here blocking the positive effect of the protons. That's not bad. I got 54 electrons here in the way, blocking the view, blocking the attraction of these protons on those 2 electrons way over there. This has a name, and it's called the shielding effect. The effect that all of those electrons, and besides that, by the way, I got all the d electrons, which I didn't even draw. Okay, but they're in that 54. It's a huge effect of these electrons, blocking the protection, if you will. Here's the protective force, way in the nucleus, 1/10,000th of the size of this atom. and those are the protection, and they're blocked by 54 electrons. Man, real simple to steal these guys. So as I go down the periodic table, easier and easier and easier to steal those. So what's going to be the easiest element of all to steal an electron from on the periodic table? Him. It's the hardest one on the whole periodic table to steal from. Yeah, him right there. And does that make sense? Sure, that's what the chart showed. And the chart didn't go all the way back. Hang on, give me 30 seconds here. Here's helium. It's the highest of everything. If we kept going down here, it's going to keep going lower and lower and lower as it gets bigger. Okay, guys, are doing great. Tomorrow, we're here. Thursday, review. Friday, test. Have a great day.
Eli, what were you trying to do? It's 34.
Real